Hello and welcome in the lecture of vibration engineering, and we are continuing with the damped free vibration. So this is damped free vibration. Today in this lecture we are going to solve the numerical which will explain that how we can get the response of a damped system. If you will recall our previous lecture, we have derived that if you are having a damped system where this K, C and M representing the stiffness, mass and damping, and I know that the zeta of this system is less than 1, that means the damping is less than critical damping. And what is critical damping? So critical damping is 2m omega n. We have already seen this. So this is a critical case, and whenever we are having this case, that means if I will disturb my system, the system will oscillate and then the vibration level will die out. Because when zeta is greater than 1 or equal to 1, the system will have aperiodic behavior, that means it will not oscillate, and when I will give certain disturbance, the system will go back to its mean position and there will not be an oscillation. For example, if I will give a displacement of 5 centimeter, the mass will come here. If I will release the mass, if the case is like critically or over damped condition, the mass will go back to mean position, there will not be any oscillation. But if the damping is less than 1, the damping ratio is less than 1, I will give some 5 centimeter displacement, so mass will go back to mean position, it will cross the mean position, it will reach back, but the amplitude will not be 5 now because the damping, it will be less than 5. In this way, in each oscillation there will be some dissipation of energy and finally your vibration amplitude will go to the 0 level. So today also we will try to solve one numerical and we will try to understand that how we can get the response of a real life system. So here I am showing a problem, a real life problem, that here this is a forging press. So how the forging press work, that here is a huge mass placed on some base. Instead of showing the base, I am showing here some springs, but actually this is not a spring, actually there are springs and damper. Not in terms of this spring and damper, there may be a concrete packaging. So the concrete will offer both dampness as well as the flexibility. Now this is a huge large mass. On this large mass there is a die, and that die there is a workpiece, and a heavy hammer drop on the workpiece so that there is a pressing of this and we get the forged component. So this is your real life problem, and what happens here, because of this huge falling of this mass, there will be some disturbance to anvil which is on a flexible support. So definitely when suppose like the hammer will come here and then go back, but because of this impact of the hammer, the anvil will vibrate. So we are here we are interested to find the vibration or the response of this heavy anvil. And what do you mean by response? Response means I am not interested only to get the natural frequency. Response means suppose the hammer will let's hammer is falling on the workpiece, and I am interested to find that after 0.5 seconds what will be the position of the anvil, or what will be the acceleration and displacement of this anvil. So my first job would be to get a mathematical model. So this is your real life problem. Here I am having a mathematical model in that the M comprises of this whole mass. Now this is K and this is C. In the question it is given that you are falling, the hammer is falling from a height of 2 meter. The hammer has a mass of M and the anvil has a mass of M. So here the data are given that the hammer mass is 1000 Newton, anvil mass is 500,000 Newton, stiffness is 5 into 10 to the power 6, and the damping is 10,000. Now if I will go back and I will see here, this M is given to me, K is there, C is there. So if I will recall, I know that I can calculate the CC, because CC is nothing but 2 under root Km or 2m omega n. That means I will be able to get omega n as well as I will able to get the CC. Now in the question it has been asked that find the displacement and velocity of M after 0.8 seconds. So that means definitely first we have to find the response equation. Response equation means we have to find an equation where x will be a function of time, and there will be equation where t will be there, so when I will change the t value, my x will change, and that will basically tell me the velocity displacement of my mass. Now my first question will be there, that whether the system is critically damped or under damped or over damped. How I can get it? I will calculate the CC value, and I will compare this CC value with the C value, so that I will come to know that whether there will be really oscillations, or the system will just there will be a displacement and it will go back and becomes stationary. So when I will calculate the CC value, my CC value will be this, and then I will calculate the zeta, and zeta is coming out 0.099. Because I will put the C value, I will put the CC value, and I am getting that my zeta is 0.098, which is less than 1. That means when the hammer will fall on the anvil, after that there will be oscillations which will die out with respect to time. So if I will be able to get the expression for the x, and I will put different t value, I will get the amplitude for different time. So now let's try to find. As I said in my previous lecture, that if you have to solve the problem, you can either use this expression or this expression. These are standard, and I would request the student to remember this equation. So this is the response equation for an underdamped system, where zeta is the damping ratio, omega n is the natural frequency, t time, a and b are constant. And as I said, that this is an initial value problem, and if I know this is a free vibration case. So in free vibration case, what happened? You give some initial disturbance to your system in terms of velocity or in terms of some displacement, or both. So when you will give this initial condition to this equation, as there are two initial conditions, displacement and velocity, there are two constant which will be able to get by putting these two values sequentially. So now this is my system, and I have to understand that whether I am giving some initial displacement or initial velocity. So if you will go back and you will see your problem, you are considering that a mass will fall on the system. So definitely when mass will fall at this stage, there will be certain kinetic energy, because when the mass will come from this side, I can calculate mgh will convert into half mv square. So my velocity when this small mass will reach to the surface of this can be it's possible to get. When this velocity will be available, as these two masses are not of equal amount, that means if I will balance the momentum, because when this m will hit this large m, there will be exchange in the velocity. So I have to write the equation for momentum balance. Here coefficient of restitution is given. Coefficient of restitution means what? Suppose a ball is falling from certain height to this body. If the coefficient of restitution is 1, means the collision is completely elastic, so the ball will go back to the same height. But if the collision is not perfectly elastic, that means after hitting the ground, and if E is less than 1, the ball will go back to certain height and depends on value of E. If E is 0, that means it's a completely plastic condition, so the mass will reach and it will stick to this mass. But in this question, coefficient of restitution is given. That means after hitting this mass, this will go back, and certain velocity exchange will be there, that we can calculate. So now let's solve the problem. As we know that we can calculate the mass, we know that this mass is falling here. So if I will see half mv square is equal to mgh, I will get the velocity of this mass, and that is coming out 6.26, because my height is 2 meter given, and m will cancel out, g is 9.8, so this 6.26 is the velocity when this mass is hitting this surface. When I will see this problem, so this when hammer will touch this anvil, its velocity will be 6.26 meter, and that will be the initial velocity to this system. Now is there any displacement? So please remember, whenever you are having such problem where something is falling on a body, or something is hitting, suppose we are having a ball here and we are firing a bullet. So when bullet will strike the ball, there will be initial velocity imparted to this ball. There will not be any displacement. And in this case, if the ball has a small m mass and this bullet has a small m mass, and this larger ball or sack has capital M mass, So if I will balance the momentum, my second equation will have m plus m condition. But in this case, as the coefficient of restitution is given and if I am going to balance the momentum, my momentum equation will say that this would be my momentum equation, where capital M is the mass, larger mass, small m is the smaller mass. So when there is a contact, and I am writing this equation for this instant where they are hitting each other, they are striking, the small m is striking to capital M. So how the velocity will exchange? So this is the before and after, but this is exchange because I have moved this other side. So when you will give the momentum balance, and you will also write the equation for the restitution using this equation 1 and 2, finally you will get that how much velocity imparted to the larger mass, and that is coming out 1.46 meter per second. When you will put all the value here, you will get this value, which will be the initial velocity to your larger mass. So now the problem becomes simple, that you are having a mass with spring and damper, and you are giving initial velocity which is 1.46 but no initial displacement. So now your two initial conditions are there. You know your m, you know your k, and you know your c. As I said that the expression for your response will be xt will be what? E to the power minus zeta omega n t a cos omega dt plus b sin omega dt. So here you know that omega d is nothing but 1 minus zeta square omega n. You should remember this formula. So you know how omega n under root k by m, zeta is c by cc, which you have already calculated 0.098. So when I will put this value here, I will get the omega d. So in this equation, zeta is available to me, omega n is available, omega d is also available. The only unknowns are a and b, which can be get by putting this initial condition. So here you can see that these are the two initial condition, and when I will use the equation, this is my equation for the response. So in this equation, at time t is equal to 0, which is the initial condition, my displacement is 0 and velocity is 1.46. So when I will put t is equal to 0 in all the 3 points, and x will be 0, so this term will become 1, this will be 0, this will become 1, so my a will be 0. So first will give me a is equal to 0. Now when I will differentiate this expression and I will put this velocity, I will get the second constant, that is the b constant. So now when I will differentiate this expression, this is my expression where I am putting that velocity, and when I will put t is equal to 0 in this expression, I will get b is equal to 0.0149. Now I know that a and b value, so I will put the a and b value in this expression, as well as the zeta and omega d value. So this is my final expression. In this expression, if I will put t is equal to 0.8, I will get x value. If I will differentiate this expression and then I will put t is equal to 0.8, I will get the velocity. So as in the question, it is asked that you have to find the response of your system. You have to find the velocity and displacement of this anvil at after 0.8 seconds. So in this expression, when you will put t is equal to 0.8, you will get displacement. If you will differentiate this expression and you will put t is equal to 0.8, you will get the velocity. So I believe that now you have one understanding that how you can get the response of a damped system using the standard solution. Thank you.